Well, yeah, hope you had a good week. I've been a bit lazy putting up exercises, but I realized that preparing slides is a lot of work, so I'd rather have my slides ready than not have no exercises. Okay, so today we'll talk about hypothesis testing. So just where we left off last week. But let me quickly repeat again what we did on Wednesday, where we discussed basically some properties of Gaussians mostly. Before we go to hypothesis testing and discuss various tests in the linear regression model. So I plan to finish here. In case we get there, we'll talk more about linear regression, more advanced things. If not, then on Monday. Okay, so, well, the first thing that we noted is that basically the product over n independent Gaussians can be written as one multivariate Gaussians, where we just construct a covariance matrix, which is a diagonal matrix, and a mean, which is a mean vector. And, well, the special case is the kind of the IID Gaussian, where all the samples have the same mean and the same variance, in which case then the mean vector is a constant mu, and the covariance matrix is identity times a constant sigma squared. Why is this helpful? Because we don't have to say everything many times for univariate Gaussian distributions or multivariate Gaussian distributions, because univariate Gaussian distributions are just a special case of multivariate Gaussian distributions. And we'll only go to univariate Gaussian distributions if we need some insights or whatever. Okay, so we said that, if you look at sums of variables and means of variables, they look astonishingly Gaussians if it's many samples. And, well, we also said that this is due to the central limit theorem, which says that if you compare the sample mean, or the difference between the sample mean and the expectation of a variable divided by square root of n, then this goes to a normal with zero mean and covariance equal to the covariance of x, so of a single sample, where this square root of n basically just is there for not having n times that, because well, if we add up n independent samples, we get n times the variance. So if each of those has a covariance of sigma, we add up n or we average. We add up n samples, then we get n times that. Well, why is that nice? Because it means that if we observe enough data and we just look at summary statistics of that data, like means, then Gaussians are usually enough. And what it also means is that if we have a pretty simple model for data which is actually quite complicated, that, well, because there's a lot of stuff in the true, like generated stuff going on, many effects that add up to the true distribution of that variable, we can basically say, well, they will average out, and in the end, what's left in the end will look like a Gaussian most of the times. So what it also means is that Gaussian is a limit distribution, which means that once we have something that is Gaussian distributed, under many transformations and many operations, it stays Gaussian. So we can basically add them, we can do linear transformation, we can look at the marginal distribution of a multivariate Gaussian, and we can look at the conditional distribution. That's something that we haven't looked at last time, but we'll do that later once we need it. And all of these things are Gaussian. So what does it mean to look at a linear transformation? Well, I mean, okay, so the first thing that we said about Gaussians is that they are described only by the mean and the covariance. And if you have any random variable with some mean and some covariance, then if you take the linear transformation of that random variable, then we can compute the linear transformation of the expectation, which is just the expectation of x times, well, it's just a linear transformation of that here. And the covariance matrix of that is also basically a transformed version of the covariance matrix of x, where now A basically appears twice, so it's kind of as quadratic in A. So, well, that's nice, because if you have something that is Gaussian, Gaussians only consist of mean and covariance. So once we can write down the mean and covariance of a Gaussian, we have all that we need to know about the distribution, because we can just look up the normalization constant and everything from the formula. So if we take a Gaussian variable, then the linear transformation of that Gaussian variable will also have a Gaussian distribution with that mean and that covariance matrix. Okay, so, well, we said also we can now use these kind of linear transformations as kind of tricks, shortcuts to look at various other things. For example, the marginal distribution, where we just take, well, okay, so first let's start with an independent Gaussian distribution, and we said that if you take the marginal distribution of that, then it comes out as a Gaussian again. Well, that's a nice observation. Yeah.
So the second line, where you have the two normal distributions, should the second one be x2?
X2, yes, yeah, X2 it's a typo, as always. I forgot. I mean, I observed this typo last time. I forgot about it, so I'll probably remember it this time. And so I always try to update it, like get rid of a few typos from time to time, but this one I still missed. Okay. Okay. So, but if we have a multivariate Gaussian, then if we take, basically we can use this trick that we can basically write the marginal distribution as a linear transformation, a pretty simple one where we just set parts of basically the part that we want to marginalize over to 0. We can find the Gaussian distribution that looks like that, and it has this form. Note that this is not a proof, but it's true, at least, and it helps us kind of to understand what we're kind of doing once we look at the marginal distribution. That we just all we need to know of the original mean, which was basically the concatenation of the two means, and the original covariance matrix, which is the covariance matrix of each part, and then the cross covariance between the two is we need only the mean of x1 and the covariance of x1 if you want to marginalize out x2. And well, for a multivariate Gaussian, what is actually marginalization over one variable? It just means that we just over one dimension here, we basically take the average density over that dimension. So it's just take the whole space. So it's an integral basically over that. Okay, so the sum of Gaussians is also Gaussian. That's we also said. I mean, it's pretty trivial. The nice thing about that is that it kind of also follows from the central limit theorem, because you can already view Gaussians as the sums of non-Gaussian, possibly non-Gaussian random variables, and these sums become Gaussian. Now, if we take the sum of two of those, we can just write them again as the original sum, and of course, the result is also Gaussian.
They have to be with the same mean. They have to be with the same mean.
Yes, but
I mean, otherwise you get.
yes. Okay. I mean, yeah. Well, these here also, in this case, we also assume that they all have the same mean and the same covariance here. Yeah. Well, if they have different means, and if they have different means, and what happens then? Okay, so if the mean also changes now, then you basically can view the mean also as a random variable, right? So basically, you can think of a hierarchical model where you first sample a mean, and then from that mean, you sample your variable that you're then adding up. Then what this means is that just the mean, the sampling of the mean, it just comes part of the sampling process, and this you can just write it again as one single sampling. Of course, if there's kind of a systematic thing where you have two things that have two different means and you sum them, then it's not the case. So it has to be random what the mean is in order for this to hold, because then the overall mean, once you integrate out that mean, is again a constant. Okay. What do we mean when we say whitening? And it's basically saying you have some univariate Gaussian, and we want to find well, an equivalent Gaussian, or equivalent Gaussian that is just a transformation of this here, which has zero mean and variance 1. And well, we can again get it by a very simple linear transformation where we just subtract the mean and divide by the standard deviation. And then we can always get from any Gaussian random variable to something that is just a standard normal. Well, in the multivariate case, it's almost the same idea. Just that here we don't have so again we have some linear transformation. Just that here we don't have a standard deviation, but the analog thing to the standard deviation, which is the square root of the variance, is now a matrix square root of the covariance matrix.
So I think you have another typo, I think. It should be x plus b first of all. Yeah. The linear transformation. Linear transformation.
B equals da.
Well, I mean, just the second bullet point, I think it should say f of x equals ax plus b.
Ax plus, wait a second. Not plus mu, yeah. But plus, yeah, that's right.
The b, should that be negative? Negative sigma to the
yes.
negative half mu?
Yes. Okay, good, very good to note that.
Why is it negative?
Because you have to subtract off something in the mean, right?
Okay.
Yeah, in order to get to zero mean.
And of course, the covariance becomes 0, 0.
Oh, I didn't see that. Okay, yeah, that's right.
Sorry.
Yeah, and that once you see something like that as a covariance matrix, it's not a covariance matrix because they are always symmetric and positive definite, and this one is neither. Well, no. Well, is it positive definite? No, probably not. I don't think it's positive definite. It's probably very easy to prove that it's not. We said in order to prove positive definiteness of a matrix, we can have to show that for every x transpose that matrix, x has to be larger than 0 for every x that is non-zero. And so if we just take x to be, for example, +1, -1, then we get a 0 here, right? It's a very easy counterexample. Okay, so matrix square roots. What is a matrix square root? It's basically just some matrix that if you multiply it by itself transposed, if it's non-symmetric, or just by itself if it's symmetric, then you get the original matrix out, or the original matrix it's n by n, so it's symmetric. And there are several ways to get to such matrix square roots. By the way, a very trivial one is, for example, if you already know that this here is x transpose x, then we also already know that x is a matrix square root, right? So if we already computed this as kind of as x transpose x, then x, of course, is a matrix square root. It's just trivial, but if we don't have that and we want a matrix square root, there are several ways to compute them. They're all usually cubic, well, all cubic in the data, in the dimensions. One is a Cholesky factorization that works if the matrix is positive definite. In this case, this matrix L is a lower triangular matrix. And of course, L transpose is an upper triangular matrix then. The other one is the symmetric matrix square root. It's basically some matrix square root that is just symmetric. So we're basically B1 half and B transpose half is the same. And we can get that, for example, from the eigenvalue decomposition of B. It's a unit matrix. And the eigenvalue decomposition is basically, well, if B equals U lambda U transpose, then lambda is the eigenvalues of B, which means that if we take, how was it? If we take an eigenvector and multiply it by the matrix, then what we get back is the corresponding eigenvalue times that eigenvector. So it's just a scaled version of the eigenvector that we get back. And well, U holds all the eigenvectors. So it's the eigenvectors are usually given in a form that is orthogonal. So it's U transpose and U transpose U equal to the identity. And you can get the matrix square root by taking the square root of all the eigenvectors, which is valid because they all have to be larger than 0 in the positive definite case, or in the positive semi-definite case, or non-negative definite case, they have to be larger or equal to 0. Interesting thing is that also you can use the eigenvalue decomposition to compute the inverse. Right? I mean, it's just you take the inverse of the eigenvalues in order to get the inverse of the original matrix. What else? You can use it to compute the pseudo inverse of a diagonal matrix, where we basically take the inverse of the eigenvalues that are non-zero. Because if you take inverses of 0, then that's not defined, but you invert just the non-zero eigenvalues and keep the others at 0, and that gives you the Moore-Penrose pseudo inverse of B, if B is non-negative definite. Okay, and what this also means is, because this part here is just the identity, is that this here is also a matrix square root. Okay, well, we said that we can use the matrix square root, for example, in order to sample from a multivariate Gaussian, even though usually we can just sample from univariate Gaussians. So usually we get samples from Gaussian with mean 0 and variance 1. And what we do is we just take the matrix square root of the covariance matrix, and in order to and then in order to get from n samples here, which we can basically view as a normal with vector 0 mean and identity covariance matrix, we multiply the identity on both sides with the square root of sigma, then we get sigma back. And then we add just a b to it in order to get a sample from a multivariate Gaussian. Okay, that was all that we did last time. Are there questions to this so far? No? Okay, so then let's go to hypothesis testing. You start with a quick introduction to that. So, well, again, in the linear regression setting, where we basically said, well, we have a vector beta. This beta is dimensionality d here, and we just take some SNP, plug it in there, and we want to test it. So it's one entry now of this beta. And a way to ask whether this variable x, which in this case is a SNP, has an influence on y, so whether it adds something to it. The question to ask is, well, is this regression weight that we attach to this one variable x that we want to test, is that equal to 0? Because if that is equal to 0, then there's no effect, which in return, if it is not equal to 0, would mean that there is an additive effect. Well, the true beta is unknown. All the other things are usually also unknown, but currently we assume that only the beta is unknown here. And well, we said, okay, let's use our maximum likelihood estimate of that and of that as a test statistic. Say, okay, if the test statistic deviates very far from 0, so if the maximum likelihood estimate is not close to 0, then probably the underlying true beta is also not 0. That's the whole idea. Right. Yeah.
So this graphical model, does it, I mean, it seems like it makes x depend, so the x's become conditionally dependent given y. Is that correct? Because you have the arrow.
Yes, that's correct. That's correct. So if you observe y, then the x's are dependent. Yes. So what's the what?
I remember the rationale.
Okay, so I mean, okay, yeah.
It's kind of similar to, for example, naive Bayes, where you have the opposite situation. Basically, the x will become independent given the y.
Yeah.
Here it seems like the opposite.
Yes, I mean the idea is so okay. So maybe does anybody know what, like everybody know what we're talking about? We're talking about that we have a graphical model here, which has a so-called V structure. So it's basically all the edges from the variables here point to one variable. If you don't observe this variable, then these are independent. But if you observe this variable here, they suddenly become dependent, which means, so what does dependence mean? It just means that the conditional distributions are not, that they are not factorized. So it's not p of x and p of that x times p of that x, but if we condition on y, so p of that x, condition on y, and p of that x, condition on y are not independent. And what's the reason for that is that basically, if they all have an effect on y, then if you observe this here, then and if you observe these two here, for example, then we observe these two, is now easier. And everything that is explained, so everything in y that can be explained by these variables here is probably not explained by these. It's an effect called explaining away. So basically, y has some variance, which is in this model. I mean, in this model is pretty clear. It's the sum of the effect of this x and of this x, right? So we have a sum of the two effects. Now, if we observe y, we observe the whole sum, but not parts of the sum. If we observe y and xn, then we observe parts of the sum, kind of, and we observe y, which means that this x here probably only explains the rest of the sum. So it tells us a lot about the values that this x can take. And that's also the idea here in statistical testing, where we say, okay, everything which we are kind of not interested in, we condition on. So it's a covariate. So, for example, in a genome-wide association study, there might be an influence on the people by sex or the race of the people. So there might just be, well, for example, the sex. If you the phenotype is height, then males are just higher than females, and so you plug the sex in here, and of course, if some individuals, if exactly the males are taller than the females, then you don't need to find genetic causes that explain the difference between males and females, because yeah. But you're only interested in the differences beyond this difference between males and females. So that is kind of this idea that we have a V structure here, that once we observe Y, we observe that males are larger than females, and we know who males and females is. This tells us something about this here. Yeah.
If we have this structure, this graphical model structure, doesn't it make the inference of the parameters like super expensive, because now you have to consider all possible basically combinations of x's in order to get the...
Oh no, it does not, because we already have agreed on a structural form for the model, which is a pretty simple one. So everything is additive. So you don't have to look at all the possible combinations. I mean, if we don't restrict ourselves to a simple linear model, then this would be true. For example, basically what you would have to look at in the most general case, for every value of that x and y, now you have kind of a matrix, you get a probability distribution over that x.
So isn't that equivalent to getting a model where you reverse the edges, so basically y n points to x for all x's? Because then you assume that, I mean, it's kind of, because you take the product here, you kind of assume that the x's are different. Or no, I see.
Well, the axis. Okay, so if you reverse the edges, right? If the axis now depend. So say, what would be an example? I mean, this is something that could happen, right? I mean, you could, for example, do. Well, why not look at, for example, race as the phenotype. And then these are different positions on a chromosome. Then, of course, race, I mean, if there's, for example, in African Americans, if there's a different inheritance pattern of one chromosome versus Caucasians, then of course you would basically have a dependence that goes from Y to X. In that case, it's exactly the other way around. If you flip the edges, then once you then if you don't observe Y, these are dependent because they are both influenced by Y. But once you observe Y, they become independent because you already know what causes them to be causes them to be correlated. But, okay.
I'm sorry, I'm actually slightly confused about the notation.
Yeah.
The XN and the XNS. Right?
Yeah, that's something that I've been struggling with a lot because I mean, okay, so this is a vector, so that's why it's boldface.
Yeah.
And I actually have this always d-dimensional or d-1 dimensional, and this has one dimension of that. And this S here is now an index of the SNP because you try out different SNPs. So I'm not happy with that, and I'm still looking. So if you have a good suggestion for the notation, then.
So the bold X includes everything except the SNP S?
Here, yes. Here, if I write it here, no. Then in this here, yes.
Okay.
Yeah.
I think Eleazar usually uses a star. He uses X star.
Okay.
The notation for everything except the SNP you're testing.
Oh, I've used X star before for this X here. I mean, because it's the one that we're interested in is the star, you know, and everything else is no star. But I mean, that's arbitrary, I guess. Okay, but here it's like that. Okay, so.
Just final question. So is it generally this the assumption in linear regression that you're going with this graphical model, or where the x's are causes of y, or
if you write it like that, yes. It's basically you. If you write it like that, yes. In reality, of course, I mean, don't interpret this as like a causal model here.
Yeah.
I mean,
I'm trying to reconcile
because
with how, for example, naive Bayes works. Exact. At this point, reverse the model.
yeah. Okay. So, I mean, one example where these are not causal is just in a GWAS, where basically you just look at SNPs that are proxy actually for something that happens in that region, but we know that there's correlation in regions. You can use something, a different SNP, to just fill in for the actual cause, for example, yeah? That you don't observe. Okay. So given a sample of n individuals, we want to test the null hypothesis, whether some regression value is 0, which is the null hypothesis, or the alternative hypothesis that it's non-zero. And, well, in order to show that this is non-zero, we need a statistical test that tries to reject. So basically we have to reject the null hypothesis in order to show the alternative hypothesis. Now we can talk about outcomes of these tests, right? I mean, so yeah, there's the case where the null hypothesis holds, or the null hypothesis doesn't hold, which means that the alternative hypothesis holds. Now, our test outcome could be that the null hypothesis is accepted or rejected. And, well, if the null hypothesis holds and we accept the null hypothesis, so we say that, well, beta is 0 in this case, so we call this a true negative because we have not reported that, that beta in this case, or that x in this case. If we accept the null hypothesis, but in reality there is an effect, so the real beta deviates from 0, but we say it's 0, then we call this a type 2 error or false negative. If if we reject the null hypothesis, which basically means that we report an association, but it holds, then we call that a type 1 error or a false positive. So I don't like this type 1 error or type 2 error because it's completely non-descriptive. I mean, it doesn't say anything what it means. It's just, you just have to know it by heart. So it's type 1 error is a false positive. It's pretty clear what a false positive is. It's not clear what a type 1 error is. But people tend to use type 1 error and type 2 errors. And also false positive report if the true beta is 0, but we say it's non-zero. So we report an association, or we don't report an association. We do report an association, and there is actually an association there. So those are the 4 categories that we're interested in. So there are 2 types of errors. And, well, there's usually a trade-off of these. So usually they come at different sorts of costs. So, for example, in a GWAS, typically if you report an association, the next step is to go into the lab and try to validate it. So obviously, if you report something, there comes a cost. And if you report something and it's actually wrong, then like some biology has spent a lot of money and probably a lot of manpower to validate something that's not there. So the outcome will say, oh, actually what you told me is wrong. So there's obviously cost. But of course there's also a cost of a type 2 error. So if something is really there and you don't find it, then you don't find it. And the question is what you want. Do you want more sensitivity or more specificity? And that's just different in different applications. Well, if we want to do a test, so given a sample, we want to say, well, we want to test whether this is true or not. A significance level defines the threshold on the sensitivity of the test. So it doesn't say anything so far about specificity. It just means sensitivity. So it equals the probability of making a type 1 error. So say we have the distribution of our test statistics under the null distribution, then our significance level alpha is just the area under the nulls, kind of the probability of, given that you actually have a true null hypothesis, what's the probability of rejecting it, or the probability of getting a type 1 error? And that is exactly this area under the probability distribution, or if that, so that is only for the case where you look at very large test statistics, or if you look at both large and small ones, then you have a so-called two-sided test, and basically here you have alpha half, here you have alpha half, and the rest is 1 minus alpha. Here is also everything is 1 minus alpha. Well, the decision is usually made on a test statistic, and we call this region here R alpha. And it defines basically the values, the region where we have values of the test statistic that lead to rejection of the null. So, well, what are basically the values? The values are just the values here on the x-axis that fall where the that lead us into that region, into the critical region. So, can be two-sided in this case. Usually we have, I mean, these critical regions are usually at the extremes of the distribution. So either it's just on one side very large values or very small values, or it's both on both sides. For typically, if you have some symmetric distributions like a Gaussian around 0, around the mean. Well, what is a p-value? A p-value is the smallest possible alpha such that the test statistic, so that the null hypothesis would be rejected. So it's the p-value is so say we get we observe a 9 as our test statistic under this distribution here, and then the p-value would basically be the smallest, or is it the largest or the smallest? The smallest alpha that we could use and still reject this, which basically means that the critical region would have to start here and go to here, and then it would be the size of the critical region. That would be the p-value, right?
The p-value is a specific alpha value?
The p-value is it's the smallest possible alpha, the smallest possible significance level such that you would reject this hypothesis. So if I report you a p-value of 0.5, that means that you have to make your alpha 0.5, which means that you would have to reject half your null hypothesis in order to call this hypothesis significant. If you give you a p-value of 0.01, that means that you could make that you could choose an alpha of 0.01, which would correspond to only making 1 out of 100 tests that are false positive. Whereas if you have 0.5, you would, in order to accept something, you would have to make 1/2 times a false positive.
So does that imply that you would have to have evenly distributed p-values for some data set? They would have to be uniformly distributed between 0 and 1.
Well, by definition of a p-value, just follows from this. So if a p-value actually is this, what it writes down here, then if all your p-values are generated for null hypotheses, then they are uniformly distributed between 0 and 1. That's correct, by definition. So if you have something that is not uniformly distributed, even though everything comes from the null, then it's not a p-value.
So if you're like computing p-values for some data set and you get smaller p-values or you get more small p-values than you should, then that probably means that it's not a good test.
Well, it basically means that either something numerically goes wrong and you did your computations wrong, or if that is actually exact, it means that not all of the p-values come from the null hypothesis. So there are many null hypotheses, and of course there are many ways to be that. I mean, it doesn't mean that you're actually reporting the right alternative hypothesis. It basically could mean that you have chosen your model wrong, that you're asking the wrong question in the beginning.
It should be largest possible alpha, shouldn't it? Because you can always have an alpha that's smaller and still reject the null hypothesis.
Correct. Yes. Yes.
So that is that.
No, wait a second. It's it's the smallest. No, it's the smallest. Wait a second. It's the
infimum is the largest.
The largest. Huh?
Infimum is greatest lower bound.
The greatest lower bound. So it's the largest one, such that you would just. Okay, yeah. So it is a yeah. I always mix up those with the argument. Okay. Okay, so, and it follows that it's just the probability of observing a test statistic at least extreme, which means that the significance level alpha, if you chose it beforehand, it just becomes the threshold on the p-value. So if you say, I want a type 1 error rate of 1%, then that is my significance level. That means that you call every p-value smaller than 1% significant. Well, the problem with this is this whole thing depends on the null distribution of the test statistic. Because, well, in order to assign p-values or in order to evaluate the significance of a test, you have to know the null distribution. And often that is unknown. The other thing that it means that, well, for every u in 0, 1, well, that the probability under the null that the p-value is smaller than u is just u. So it's uniformly distributed. That's what we already said. And well, okay, so p-values are uniformly distributed over the probability of the null distribution. But we don't know this distribution typically. Well, if you look at this, we said the p-value is the largest possible alpha value that you would have to give in order to reject that. And we defined alpha as this area here, which is just, if you view it as a probability, it's basically an integral over this part of the density. So it's the probability of observing something in here, which is basically, well, basically it's this area over this area, right? So it's a probability. So if you just throw random things into this area, it's the probability of landing here. No. It means that here p-values get smaller at a much faster rate than here, because the density here is much smaller. So it's the actual area that counts. So if you go a little bit further right here, p-values get much smaller than if you go here. I mean, so it's this area. I mean the area over the whole thing is 1, right? And alpha is basically the size of the critical region. It's the area it's the integral over the probability density in this critical region, and and for for every test statistic, the p-value is the largest possible alpha, such that I would still reject it, which basically means that I have to place alpha such that it's directly there, which means that alpha is the probability of observing something that is larger under this distribution, which is a uniform thing. Take it for granted.
Is there a significance to the p-values being uniformly distributed?
That they're being what?
Is there a significance to the fact that the p-values are uniformly distributed?
Yes, it's actually quite useful in practice. Because say I give you a bunch of p-values. If you now know that all of these come from the null, then you can just compare these p-values to a uniform distribution. And if they don't look like a uniform distribution, then you can tell me, oh, you didn't give me p-values. You gave me something arbitrary.
You can also, well, I guess an extension of it would be if you want to like generate random numbers from some weird distribution, you can do like a cumulative distribution function, which is similar to a p-value, like the probability of any given point would be equal. Like a CDF should be equally distributed also, right?
The CDF should be equally distributed also. I mean, the p-value is basically it's the CDF, right?
Yeah.
It's 1 minus the CDF of that distribution, because it's the CDF. It's basically something up to x, and the p-value is from x to the rest. Yeah. So it's CDF. We'll see later what that is. The cumulative distribution function. It's defined as it's just defined as this. So basically, the CDF up to here would be the probability of observing something up to here, which is equals to the integral over that part. So how do we get a null distribution? One thing that I already showed you is that we can basically repeat the experiment in a way that we know that everything comes from the null. And one way to do that is by permuting the data. So say this is the x that we want to test. These are all the others. Then we can permute y and x in the same manner, keep them in the same order, but than these, and repeat the whole computation. Then whatever dependence then between these variables and y was in the beginning is broken in that moment, right? So whenever, even if y is a function of this, if y is xs times beta s plus something else that depends on the covariates, well, if we move that y up here, then it doesn't see ever this beta. So if we test it to this x, there's no dependence anymore. So basically, we just repeat it m times. We permute the data such that the covariates and the phenotype are together, stay together, and now compute these empirical null distributions. We do that many times. And then now we can take this empirical distribution and just kind of look up how many more extreme values we observe. So we can read off the quantile of our actual tests in that empirical null distribution. So it's a fraction of these empirical nulls that is larger than, or more extreme. That gives us the p-value. So it's the amount of mass. So if, for example, we observe if our real test statistic is an 0.1 1.7 or whatever here, then basically we know that, well, we observed that many larger values at random. So this tells us the area. Basically, we can now compute the integral here over this, well, where the integral is just an average over these over the whole thing.
So it gives a good estimate of the false positive rate then.
That gives you an estimate of the false positive rate. Gives you an estimate of the false positive rate. Not really. It tells you, well, maybe you can compute one from that. But what it tells you is if these basically all these permuted values are kind of observed nulls now, and if I observe many thousands or even millions of nulls, then if I plot their distribution, it will be very smooth, and it will basically look like the null. It will reach the shape of the null. So now, if I want to basically look up the probability of under the null observing something more extreme than what I've observed originally, I just have to count. I just have to see how many are there that are more extreme. And then the ratio of the number that are more extreme over the whole nulls that I've generated is now the probability of goes to the probability of observing something more extreme, which is the definition of the p-value. Right? So that's one simple way to compute, if you don't have the distribution, just create a random distribution. Of course, it depends on, you basically now plug in this permuted distribution as your null. So if this does not really correspond to your null hypothesis, then this is also not the right thing to do. But so that is kind of a caution with this procedure. By doing this, you basically say, this is now my null distribution. Okay, so but let's go back to the linear regression model. Let's try to find an analytic solution. Well, we said that the null hypothesis is still that this is 0. And we have an estimate. So can we basically use the intuition that this estimate is a linear transformation of a normal distributed variable, namely y. So the phenotype in this model is normally distributed. That's something that we wrote down. Now, we say that this is the null model. So under the null model, this is the distribution of y, and we also have something under the alternative model. But we know that under the null model, we say that the one beta corresponding to xs is 0. And we can just plug this into here, and then we take our maximum likelihood estimate, which is just the pseudo-inverse of x times the phenotype, and compute its probability under this distribution. And because this distribution is a Gaussian distribution, if you view this as a random variable, it's just, this is a Gaussian distributed variable. This is just a linear transformation of a Gaussian distributed variable. So whatever we used as a matrix A before for these linear transformations is now this x transpose x inverse times x transpose. That's our A. So, well, y has the mean x beta. So we take x beta, multiply it by that. Y has covariance sigma squared times identity. Sigma squared times identity. We multiply it on both sides by that. Clear? So, we use basically our null model says y is Gaussian distributed with mean x beta in brackets where 1 beta equals 0, and with this covariance matrix. So if we take the data and just multiply it by an arbitrary matrix, then we can say that it's also a Gaussian distributed variable and can compute its mean and its covariance matrix. Now, we can simplify this a bit, because this is x transpose x, and this is x transpose x inverse. So we actually see that the mean of the maximum likelihood estimate is just beta, because this cancels with this. Right? And here you also have an x transpose x inverse and x transpose x here. We are left with 1 x transpose x times the variance of y. So this is the variance of y. This is the covariance of the, remember, this is the whole vector of beta so far. It's not one entry, it's the whole vector. So it's all the regression weights. Yeah?
So the capital Xn is like all the genes, which...
I know also this is plugged in. That's why I always say I'm not happy with the notation, because I separate this out here in the graphical model, but whenever I do some equations, it's one of them.
Right.
So this basically, this X is the matrix of concatenating all the n xn's and all the n xn's.
This little x and s is the particular SNP we want to know if it's responsible for the phenotype.
Yes, correct. Which is just one column of this matrix X.
Right. And then, so the beta S being 0 would be the null hypothesis? Like the
Yes.
SNP is not responsible?
And we now compute the distribution of the maximum likelihood estimator under the null hypothesis, which means that one of these betas here is 0, the one that corresponds to the one that we're testing. So this is the mean of y under the null hypothesis is x beta, where one of the betas is 0, the one corresponding to that column in X. And the variance is sigma squared times the identity. That's the null hypothesis.
Okay.
It's just taking that y given X. Now, we use that y, which is a Gaussian distributed variable in the null, under the null, and compute a linear transformation of it, which is our estimator of the betas. And we see that the distribution of that estimator under this null hypothesis, so basically if we observe a data set of n points, then the distribution of the maximum likelihood estimate computed on that data, on those n data points, is just follows from the distribution of those data points. So it has a mean, which is so basically the expectation of the maximum likelihood estimate goes is the true beta, which means that the differences in the expectations of beta and the true parameter is 0, which means that it's an unbiased estimate. So if you have heard about bias and unbiasedness, so the parameter is unbiased if its expectation under the true data distribution follows as the true parameter. So the maximum likelihood estimate is an unbiased biased estimate of beta. And its variance follows from as a linear transformation of the covariance of y under the null, which is the variance times the identity and multiplied by both sides by the linear transformation, where some parts cancel then, so we're left with x transpose x inverse times the variance. All right? Now, well, now this is just canceling out all the x's that we don't need from the equation before. So this is now the distribution of the maximum likelihood estimate. Where this is the true beta, this is the true variance of the data. And, well, in our test, we're only interested in one in one entry of this vector. So let's just use the marginal distribution. And we said, how can we do a marginal distribution in a Gaussian? Well, we take the whole mean, and we only take the one entry in the mean that we're interested in, which is beta s, null, which is a 0 under the null hypothesis. And, well, out of the whole covariance matrix, we now just pull out the diagonal entry which corresponds to the variance of that beta s. Now we have got, for this one entry, under the null hypothesis, a normal distribution which has its mean and its variance. We're not interested in all the other entries, so we marginalize them out. And this is the marginal distribution. Is this clear?
The ML is maximum likelihood?
Yes, that's the maximum likelihood estimate. Well, okay.
That's just the coordinates of SNF.
Yes, yeah. I mean, it's the one corresponding. Yeah, as I said, I'm really not happy with the with these betas here with the beta notation. It's a little bit. It has to do also with other parts of that lecture where I used basically all the SNPs to be in X and then and in beta and then so and here I'm swapping them out. So I probably should not try to have the notation consistent between the two lectures and just have them locally more consistent. Okay. Okay. So well, but it now means that for a given data set we know the probability distribution of this beta. Well, now what is the p-value? We said that the p-value is the probability of observing something at least as extreme, and as we said before, we can get that the probability of observing some variable that is some value for the random variable that is well smaller or equal than a variable is the cumulative distribution function. So it basically means for this distribution, we know the cumulative distribution function of observing, for example, under this blue Gaussian here, the value minus 1 is the integral over all this density over all the values that are more extreme to this one, or in the negative sense, and basically it's the integral up to minus 1. And then what we get, because the integral from minus infinity to plus infinity is the integral over the whole distribution, so that's a 1. So it's something that starts at 0 and goes up and then goes to 1. That's the cumulative distribution function. And well, for the univariate normal distribution with mean and variance sigma squared, the cumulative distribution function looks like this. Where this is the so-called ERF. What's ERF again? Well, it's the integral over the standard normal, basically. It's the error function. The error function, yeah. It's just the Gaussian integral. Now, just, I mean, don't care about it. Just call it in a computer if you need it. It's just if you plug x in there, then you will get for different x's, then you will get something that looks like that. Goes from 0 to 1. So it's the integral from minus infinity up to x over the normal distribution here. So it's the integral of y up to from minus infinity up to x is a function of x only. Now, okay, now we know now we know normal distribution in beta, the mean and the variance. We know this cumulative distribution function. Now, in order to get the p-value, basically we have to see what's the probability of observing a value at least x extreme, which means, well, a Gaussian is a symmetric variable. We said, okay, we just want to exclude something that is close to 0, so we have to with at least x extreme, it means it can either be a positive value that is more extreme or a negative value which is more extreme. So we actually need something in 2 times the minimum of the cumulative distribution function and 1 minus the cumulative distribution function. Because the cumulative distribution function starts at here and then goes to 1. But if it goes to 1, it basically means if we wanted to start at plus infinity, well, we could also just flip this around and start at 0 and then go to 1. Yeah? So now, just using mathematics, basically, and Gaussian calculus, we have computed the p-value for the maximum likelihood estimate. But, okay, so this distribution here depends. The distribution of the maximum likelihood estimate has the 0 mean, has a variance which is equal to the variance of the data times this entry here in the covariance matrix of the betas, which corresponds to variable z, which is standard normal distributed, where this is just, we just used this this transformation where we basically subtract the mean, which is a 0, divide by the standard deviation, which is the square root of the variance, right? So it's the square root of this, which is the standard deviation of the data, times the square root of x transpose x inverse of that entry of that matrix. So this gives us something that is standard normal. So what's the problem with this? Does anybody see it? Just read the slide if you want. Try hard. Okay, yeah. So, well, the problem is that we used the data variance, which is an unknown parameter. So in reality, so basically we have now a distribution of our data which contains parameters that we're interested in, like this beta here, because we want to do a statistical test on this. But it also contains other parameters that we don't know, that need to be estimated, but they're not interested in those. And that is what we call a nuisance parameter. So beta would be a parameter of interest, and this would be sigma squared, for example, would be a nuisance parameter. We've already gotten rid of all the other betas, but this here we cannot easily get rid of. Well, so in practice we have to estimate it somehow. And, well, one estimate is the sample variance of it. And so basically we can use this estimate, which is basically 1 over n minus d, where d is the dimensionality of the maximum likelihood estimate of the beta. So it's kind of this corrects for a loss in degrees of freedom in estimation of the variance, because we are already regressing parts of it out with this beta. And then it's basically just the sum over the squares of the regression errors of that. Right, and now we can plug in this into this distribution, which is possible to do, but it's not ideal to do. So the problem is that the sampling distribution now, it should not depend on nuisance parameters. So it means that if we plug this in, this Gaussian is not really correct. For large samples, this is not an issue because, well, if for n equals n to infinity, this will give us an unbiased estimate of the sampling variance will give us an unbiased estimate of the true data variance. So, so if you have a very large data set, this Gaussian will do all right. For a small data set, it's not ideal. And well, that's what some guy who worked for the Guinness factory studied under the pseudonym student. So he developed the student t-distribution. And it turns out that if you want to get rid of this variance, if basically the variable t, which is the variable z over z over the sampling variance times the sampling standard deviation times the standard deviation. Remember, z has the standard deviation of the data, so these standard deviations cancel here. So it's just a way to write. If we basically, I mean, this just means we take this here and replace that data standard deviation by this one, right? Sorry, this is, by the way, squared, it's not a lower script 2, it's an upper script. So if this here depends on the true standard deviation. In order to get rid of it, we multiply again by the true standard deviation. Now we divide by that. So it's just taking this variable here and replacing the data standard deviation by this. And it turns out that this has a t-distribution. I don't want to talk very much about the t-distribution, but no, it has a parameter which is the degrees of freedom. And the t-distribution for infinite degrees of freedom goes to a standard normal. So infinite distribution, and the degrees of freedom are basically n minus d, which is the number of data points minus the number of regressors. And we said also that this now it basically corrects now for this additional uncertainty that we have in these nuisance parameters. And for n equals infinity, this goes to the true variance. And also turns out that for the degrees of freedom, for n equals infinity makes the degrees of freedom infinity, this just becomes a standard normal distribution. So in that case, if you plug in the t-distribution, the normal distribution becomes exact. For small number of degrees of freedom, the t-distribution has wider tails than the Gaussian distribution. It just means that, what does it mean if it has heavier tails? So this is just the infinite, which is the standard normal. Now if we increase make the number of degrees of freedom smaller, 5 to 1, then just here at the border of the distribution, it goes up, while here in the center it goes down, which means that there's more mass far away from the mean. It just means that you can observe more outliers under this distribution if it has heavier tails. Otherwise, it looks very similar to a Gaussian. Yeah. And just that this doesn't look very magical. There are basically some simple relationship between these distributions. Say x is a normal distributed variable, then basically z scores. So it's basically z score is typically x minus the mean over the standard deviation, and this is a standard normal. If we now take a standard normal and take the sum of squares over IID standard normals, then we get something that is called a chi-squared distribution. So the sum over n of these 0, 1 normals is a chi-squared distribution with n degree of freedom. We take the ratio of a standard normal and an independent chi-square, we get something that is student t-distributed. And what this basically, so that's a way to get to this student t result. We basically had this z here, which was standard normally distributed, but we had to divide by something else. And it turns out that you can prove that this something else is chi-squared distributed, the sample standard deviation. So it's a square root of a, it's a square root of a chi-squared times the square root of over the square root of n. That is a student t distribution. So that's just a way to get to the student t result. If you look it up in this formula, this is Wikipedia basically.
Oh, okay. Is there any like intuition behind that? That relationship between the student t, the standard normal, and the chi-squared?
Not really. I mean, it's I don't know of an easy intuition. I basically it's just pattern matching. So.
Yeah. Okay.
Well, another interesting distribution that you might observe is the ratio of two chi-squared distributed variables that are independent is what we call an F distribution, where we have n1 numerator degrees of freedom and 2 denominator degrees of freedom. Another thing is, in order to get from a normal distribution to something, if you take a normal distributed value and just take its square, right? We said that our beta is normally distributed. If we take our beta squared, then we have something that is chi-squared distributed. If we now take our t distributed variable and take the square root of it, we said that we have something that is chi-squared distributed on the top, something that is independent and square root of a chi-squared on the bottom, which means that we have the ratio of 2 chi-squared. So if we take our t statistic here and square it, you get an F distributed variable with numerator degrees of freedom 1 and denominator degrees of freedom n minus d. Just some magic.
I have a question about this t-test. So
Yeah.
that sum, why does it go from 2 to n plus 1?
Um,
I see why it doesn't include n equals 1 because that's so unpopular.
Well, it's
Include that, but
because it's supposed to be. I just did it like that because I wanted to say that these sets are samples from a standard normals, and I want to make clear that these here that are being summed up are independent of those, so that I mean I just wanted the indices to not overlap. So Z1 and
okay.
2 to n plus 1.
So it's still n standard normal.
Yes, it's just n standard normals that are different from this one. And the same thing here. Here basically I have n1 and then the start index with n1 plus 1 and go to n1 plus n2. So it just means that this sum is not the same as this sum. Yeah. Okay. Shall we do a short pause or shall we just keep on? Because it's already pretty late. Yeah, let's just keep on and then be over at some point. Okay, so another way to test, so this is another test that you will observe, is the so-called likelihood ratio test. So basically, if you now write down your null model and your alternative model, then you can also compute the likelihoods over under the null model and under the alternative model and compute the ratios of the two. So your alternative model is a little bit more complex than your null model. So you know that if you maximize this, you can maximize over one more parameter than here, because here one of the betas is equal to 0, while here they all can be whatever. So this likelihood here will be higher than this likelihood, right? And now, if this is now, if they would be the same, it would be a 1. If this goes much larger than 1, then you know also that this is kind of, it's probably more likely. So the larger this ratio between the two, the less likely becomes the null distribution again, the null hypothesis again. So this ratio tells you also can also be used as a test statistic. Well, equivalently, we can go to the log likelihood ratio. So basically, just take the log of the two things of the ratio, then we get the difference. Now it's the the alternative log of the alternative likelihood minus the log of the null likelihood. Now this is bigger than this, so this is a positive number. And now again, I skip the math, just go to the result, and I say that for n going to infinity, so it's an asymptotic result, 2 times this log likelihood ratio follows a chi-squared distribution with 1 degree of freedom, where the degree of freedom basically follows as the numbers of parameters that are different between these two models. So this parameter has 1 free parameter more than this model. This gives me a 1 degree of freedom chi-squared. A way to understand this chi-square, we said that a chi-square is basically a square of a Gaussian, right? And you can come from basically, if you take the log likelihood ratio and you go to the max, now you do a Taylor series expansion, you will actually get back our other test that we did before. So this is kind of a way to verify this chi-square result. Otherwise, and again, this chi-squared is only valid for large samples. And now the p-value is 1 minus the CDF of chi-squared. So in the chi-squared case, we don't do a two-sided test. We're not because it's always something positive. So we want something that is only larger or equal, not also smaller. So it's now we just have to take the integral from there to infinity. So it's 1 minus the CDF instead of 1 minus 2 times the minimum out of the two things, the two ends. Right. So this is just another test that is very common. Okay. There's not much more to this. I mean, I just wanted to introduce the likelihood ratio test because I might use it at other points in the lecture. Okay, so we said that the significance level alpha equals the probability of making a type 1 error, right? Well, in GWAS, not only in GWAS, but in many applications, we don't test a single time, but we test many, many times. So here, in a GWAS, we do something in the order of 1 million tests. Test every mutation to a phenotype, do 1 million tests. Well, if all of these actually were null distributed, then at an alpha of 1%, we would expect something around 10,000 false positives, even though nothing is really positive. Where basically I use S as the total number of tests, and S0 as the number of tests where the null hypothesis holds, and S is the total, so S minus S0 is the number of true alternatives. Well, say all the tests are independent, then you can just compute the probability of at least one type 1 error. So it's the, which is just, so the probability of making a type 1 error is alpha. So the probability of at least one is 1 minus the probability of making no type 1 error, which is 1 minus alpha to the power of S0, because for every of these S0s, right, we have to make no type 1 error, which is 1 minus alpha, because alpha is the probability of a type 1 error. So 1 minus alpha is the probability of no type 1 error, that S0 times. But, well, this is because this is still a number that is smaller than 1. If you do if you do a high power, then this goes to 1. Basically, this part goes to 0, we get a 1. So what this means is that basically individual p-values of 0.01 have no meaning anymore once we do so many tests. And this is a scenario that we call multiple hypothesis testing. It just means if you basically test often enough, you will just find something, just by chance. So we need to take that into account. And one way to take that into account is by using going from the standard significance level on each test to the family-wise error rate. We said that that alpha was the kind of the error rate, was the probability of making a false positive. So that's a type 1 error rate. Now we use the family-wise error rate as the probability of, well, if you take all our null hypotheses together to make a single, at least one mistake in all of these. So now the family-wise error rate is the probability of at least one type 1 error. And now what we want to do is we want, instead of bounding the type 1 error, we want to bound the family-wise error rate. And one way to do that is Bonferroni correction, which is just we take the original p-value and we multiply it by the number of tests. It's very crude and simple, and but you can show that it will bound this family-wise error rate. Equivalent to that is, instead of calling the p-value significant if it's smaller than alpha, we call it significant if it's smaller than alpha over the number of tests that we did, which is now a very small number. Right? If this is a 1 million and this is 0.01, then it's 10 to the minus 8. And well, we can show that this bounds the family-wise error rate by alpha. So now instead of saying that for each test the error rate is alpha, the probability of making at least one mistake, type 1 error, is alpha. And how can we show that? Well, we just plug in Boole's equality, basically. So this is a union of events, right? Which, of course, the probability of a union of events is smaller or equal to the probability of the sum of, smaller or equal than the sum of all the probability of the individual events. It would be equal if all the events are disjoint, but if they are overlapping, then it's a larger, right? So this is Boole's inequality, and well, what is the sum here? If all of these have a probability of alpha, because we said the p-value is uniformly distributed, so the probability of observing a null test that is smaller or equal to alpha, has a p-value smaller or equal to alpha, is just alpha, right? And we said we have S0 null hypothesis, so it's S0 times alpha is this probability, which, well, S0 is unknown. So this is smaller or equal to S, the total number of tests. Right? So the total number of tests times alpha is larger or equal to the actual number of true negatives, the actual number of negatives. So if you divide alpha, or if you divide alpha by S, then we control the family-wise error rate. That's all that it means. This inequality here. Yeah.
I'm confused by the probability of at least one type 2 error. So
Sorry, it's a type 1 error. Probability of at least one type 1 error. Sorry. Would be cool if you could. I mean, if you make a list of the typos, can you put them in an email? That would be really cool. Because I will probably remember about 1/3 to 1/2, or maybe something between 1/3 and 2/3 of them, and then forget the rest. Yeah, I don't have it, but there's a.
We'll watch the tape and go back
Right.
So do we actually use Bonferroni correction in US study?
We use typically Bonferroni correction, yes.
Okay.
That's the majorly applied approach. But I have to say that it's actually very conservative because, well,
I think if you use this one, your p-value will be very small. So
yes.
you will find much less significant.
Much significant SNPs?
Much less.
Much less significant. Yes. I mean, the p-value needs to be very small in order to be significant. And that's, of course, very few. And that is because we said, well, among the 1 million tests that we do, we want to bound the probability of having one false positive to be equal to alpha, which is typically something between 1% or 5% or so. So that's a lot. And because this is basically, because we're doing so many tests, and actually it's often, if we have some, usually we want to trade off this sensitivity versus specificity. So this is like a really, really stringent trade-off where we say, okay, we completely want to be specific. We don't want false positives at all. To say, okay, we're doing many, many tests. So as long as you give me enough positives, I'm always fine. True positives, I'm also fine if there's occasionally a false positive in there. Then what we want to do is bound the false discovery rate instead of the family-wise error rate. So what's the definition of the false discovery rate? It's the expectation of the number of false positives over the number of positives. So the false positives plus the true positives is everything that we call significant. So it's basically give me results that say if you say we want a false discovery rate of 10%, it means that 9 out of 10 discoveries that you make have to be right, and 10% can be wrong. That's what it means. Well, okay, so just a quick caution. If this is always true, if the null hypothesis is always true, then well, we just have the number of true positives is just the number of, it's just a 0, so this ratio is just a 1. So if everything comes from the null, then the false discovery rate cannot be bounded. This is all that it means. Because then it's always 1. But a more precise definition for that takes account of this is that well, there are actually some you condition on that there are also actually some cases where the null hypothesis doesn't hold in your data set, which is the sum of false negatives and true positives. In which case you can actually bound it, because you can just, you want a positive, you just make it a true positive somehow. So you have to tweak your algorithm that it makes it a true positive. And then you can bound the FDR. Okay, so false discovery rates are actually not, I mean, the Bonferroni correction was really easy, right? False discovery rates are a little bit tricky to bound. But there's an algorithm, it's the so-called Benjaminin-Hochberg procedure. So say we're given a cutoff alpha. The first thing that we do is we sort the p-values. Then, well, if we sort the p-values, if we start from the smallest p-value and go to the larger ones, then we will get something like that. We have many p-values that are very small, and then at some point we'll get some that they get larger, right? I mean, over time. Sometimes they go to 1. And we know that for the null hypothesis, they're kind of uniform distributed, so they go to 1 linearly. And for the alternative hypothesis, they're hopefully very small, the p-values. So we hope that on the left side there are a lot of alternatives, and then later there are many nulls, and kind of the distribution versus the rank is supposed to look a little bit different between these two.
So the reason why this isn't used in GWAS is because you have a lot of population structure and you have a lot of really low p-values?
I actually don't know why it's not used in GWAS. I think it's just not that broadly accepted, the false discovery rate. It's used a lot in EQTL studies, so which is a genome-wide association study of gene expression. Just because if you do gene expression, usually you measure gene expression of all the genes in the genome, which is tens of thousands. So basically the number of phenotypes is tens of thousands, and the number of tests that you do for each of those phenotypes is 1 million. So that's a huge number, and Bonferroni correction would be even more. I mean, you wouldn't find anything anymore. So that is why, in this case, you have to use something that is less stringent, and they usually use false discovery rates. Well, okay, so let's look at the false discovery rate, right? I mean, the false discovery rate, we said it's the expectation of the false positives plus the number of positives, where now if we basically at a given I, so we just take the I as the index of the sorted p-values, we know that all the p-values of smaller than I are smaller. So if you call everything up to their significant, then we know the number of positives because it's just I, right? We have called I significant. We call this one significant, and everything that's smaller. So that is the number of false positives plus false negatives is I at that point. The thing that we don't know is the expectation of the false positives in there. Well, the number of false positives is in expectation because p-values are uniformly distributed under the null. So the expectation of that is just the number of false hypotheses in the data, the number of null hypotheses in the data, times the p-value that we have up there. So that's kind of our expectations of the number. So if you are currently at a p-value of 0.1, then, and we have 10,000 data in p-values in total, then the number of 10,000 null hypotheses in total, then the number of null hypotheses that are expected to have a p-value smaller than 0.1 is a tenth of 10,000, right? Because it's uniform, they're uniform. So if at a given cutoff, the expected number of p-values smaller than that is just the total number over the p-value, because it's uniform. So it's S times the p-value at this is supposed to be an I. Is this clear? So we have something that under the null, if you have 10,000 p-values that all come from the null, then if you sort the p-values, you should basically get just a straight line that goes from 0 to 1, because they're uniform. So you should basically 10,000 times the p-value should get the number of the expected number of statistics that are smaller than your p-value, that are more extreme, because of this uniformity. So, well, take uniform distribution between 0 and 1, right? 0, 1. This is a uniform distribution. Now, if I take all these values and if I get 10,000 p-values and I sort them and I plot the index versus the p-value, well, if the index here goes linearly, and the p-value also goes linearly in expectation. So we get something that is a straight line. So at a given point, it's the number total, which is this here, times the p-value that we look at. It's just a so the p-value kind of is the slope of this line. Okay, so but we don't know S0, so in order to upper bound this, we take S instead of S0. So the total number of tests. Now, what we do is say, okay, we now we look at the number of, okay, so we maximize over I, so we try different i's from small to large, such that the index over S, so that's our estimate of that's the estimate of 1 over the number of false positives times alpha is smaller than the p-value. And once that is, so it's the largest index such that the p-value at that index, the sorted p-value of that index, is under that straight line. So if we take this sorted set of p-values, we go up. Well, in the beginning, they're probably all a little bit larger, but at some point, because we have so many alternatives, they stay small. So we are actually below the. When we go up again over this straight line, you see that if we increase I, this just is a straight line, right? That's this blue straight line here, where the slope is given by alpha. Now, at some point, there are not so many alternative hypotheses anymore, but everything is null hypothesis. So at some point, I will be just I over S. Basically, at some point, I will just have a slope from 1 over S. And here I have a slope from 1 over S times the number of false positives that I want to allow. And that is the point where I set my cutoff, because I know if I set my cutoff here, and I report these, I will get a number of positives, true positives, that is 1 minus alpha, or the number of false positives that is expected to be smaller than alpha. So I basically reject everything that is smaller, so I call all of these significant. Well, and we can show that, I mean, this is basically already the intuitive proof here, that this bounds the false discovery rate, where we say the false positives plus the true negatives is S0, false positives plus true negatives, false positives is a negative plus a, so basically the S0 over S times alpha. So the false discovery rate for this procedure is smaller than S0 over S times alpha, which is smaller than S. So this is just going from here to here, because we replaced S0 by S. Okay. And that's probably where we... let's quickly discuss what a Q value is. So the definition of a Q value is the minimum threshold, the minimum alpha, such that a given p-value would be significant. So before we had the definition of a p-value, which was the maximum significance value such that this p-value would still be significant. Now it's the minimum FTR, such that can be achieved. No, wait a second. It's the minimum FTR that can be achieved for any threshold that is larger than the p-value, right? Yeah. The minimum FDR that can be attained while still calling this feature significant is the q-value. And once we have computed this algorithm here, we can basically just read off the q-values by looking at, because we can, for every index, we get the FDR at that index. That's what we computed before. For every p-value, we get the FDR of that. Now, if we go to the right, then it might happen that we observe a smaller FDR if we call more significant, right? Because, for example, here, here the FDR gets worse, but here it gets better again if we can call more significant. So if we go further right, we can improve the FDR actually by reporting more, because we report more in that region, more positives. And now, just by looking up at that table where we get the expected FDR at each threshold, and taking the minimum FDR such that this would be significant, this is what we call a q-value. And now we can place also, so basically you can use these q-values as an alternative to p-values. Yeah. Tricky. Took me about 3 hours to understand this properly. Okay, so this should be where we quit for today.